Hello guys, and welcome to another calculus video. In this video we're going to be taking on this amazing integral right here that I have recently discovered. It looks like it shouldn't be solvable at all because we have a trig function subtracting an inverse trig function, but I can guarantee you guys that this is actually very doable, and it's quite an amazing result and very surprising. So anyway, without any further ado, let's jump straight into the integration. So the key here is to figure out how we can connect the inverse tangent function with the sine function. Because this 1 over x squared is something that we often see in integrals from 0 to infinity, and it's not too hard to deal with in general, especially if we use something like the Laplace transform. But again, the most important thing that we have to remember here is to figure out how to relate inverse tangent of x and sine of x. And the key to this is through the Laplace transform. So if we take the Laplace transform of sine of x, we're going to get 1 over x, or I guess it's s squared plus 1. And if we take the Laplace transform of sine of ax, we're going to get 1 over, or sorry, we're going to get a over s squared plus a squared. All right. Now, the cool thing about this is that this right here is a form of the derivative of inverse tangent of x with respect to s, or inverse tangent of s with respect to s. It's just kind of shifted over a little bit. And the great thing about Laplace transforms is if we want to integrate this, it's really simple. We just take the Laplace transform of sine of ax over x. I'm going to go ahead and go back to sine of x actually in this case. So we're just going to leave it like that. And that's going to end up just being the integral from s to infinity of 1 over u squared plus 1 du, using the properties of Laplace transform. So I just took this, I'm going to integrate it from s to infinity. And this ends up being inverse tangent of 1 over s. Now I'm going to go ahead and change my variable name to x here to t here to not confuse us too much. Because now I want to get inverse tangent of x. Right now I have inverse tangent of 1 over s. Now another interesting property of the Laplace transform is that Laplace transform of f of at is the same as 1 over a times f of s over a if f of s is just the Laplace transform of f of t. Right? So if I want to put an x in the top here, I just have to take the Laplace transform of x times t, or f of x times t rather than just f of t. So in this case, our f of t is going to be sinc of t. So sinc of t equals f of t. So we're going to have Laplace transform of sinc of xt. Again, this is the Laplace transform with respect to t as our integration variable. So this is going to end up being 1 over x times inverse tangent of x over s. And if we let s equal 1, then we're going to get an inverse tangent, which is exactly what we have in our integral. So let's go ahead and substitute that in real quick. We're going to get the integral from 0 to infinity of 1 over x times inverse tangent of x over s. And then at the end, we're just going to plug in s equals 1. And we're also going to subtract sine of x, and I'll bring this x outside as well, all over x. Now, reminder that this is the Laplace transform of sinc of xt, and this is just sinc of x. So I'm going to go ahead and substitute in sinc of x. So one thing that we have to remember here is that we actually need to be able to take the inverse Laplace transform, right? And unfortunately, there's nothing that really gives us, when we take the Laplace transform of something, there's nothing that will give us something that's constant with respect to s. The only exception to that is the delta function, delta of t. But we want to stick with continuous functions so that we can exchange the order of integration and take the inverse Laplace transform nicely. So we need to be able to take the Laplace transform of this term, or the inverse Laplace transform of this term, but also of this term. And the easiest way that we can do this that will give us a nice and easy to work with result is just multiplying by 1 over s, because we know that we're going to set s equal to 1 at the end, so we don't actually change the value on the right here. The other reason why we're multiplying by 1 over s is that once we take the inverse Laplace transform of this, we're going to get a sinc function, and now if we take the inverse Laplace transform of this, we're also going to get a sinc function, so we're going to end up with a Frullani integral. So let's go ahead and do that. So let's go ahead and take the inverse Laplace transform on both sides. When we take the inverse Laplace transform, we're going to get a function of t on this side. We're going to get the integral from 0 to infinity. Again, we can interchange the integrand and the integral and the Laplace transform because both of them are integrals, the inverse Laplace transform, because the inverse Laplace transform can also be defined by an integral. So in this case, the inverse Laplace transform of this term, we can ignore that x in the bottom since it's constant with respect to s. So we're just going to end up getting sinc of xt, as we showed in the previous slide. And for this, it's just the inverse Laplace transform of 1 over s, which is just 1, and we're going to subtract sinc of x all over x dx. And this is what's called a Frullani integral, so if you don't remember, a Frullani integral is integral from 0 to infinity of f of ax minus f of bx all over x dx. And just using some simple Feynman integration, it's easy to show that this is equal to f of infinity minus f of 0 times ln a over b. So in our case, sinc of infinity is just 0. Reminder that sinc of x is the same as sine of x over x. And sinc of 0 is just 1. So that means we're going to be multiplying by -1 times natural log of a over b, but in this case b is just 1 because we just have sinc of x, so it's just going to be natural log of a, which in this case our a value is just this t, so minus ln t. Now all we have to do is take the Laplace transform on both sides to get f of s back, and we find that f of s, now this Laplace transform is something that I've taken on many different videos, so you can go ahead and check out some past videos to see that. I'll try to link something right here, but just using basic substitution or by differentiating the power rule for Laplace transform, it's easy to see that this is going to end up being gamma plus ln of s all over s. And of course, as I said, we're going to plug in s equals 1 in order to get our original integral back. So that means that f of 1 equals the value of our integral, which is just gamma, or the oily macaroni. I hope you guys enjoyed this video with some awesome identities, some Laplace transforms, inverse Laplace transforms, and yeah, just a lot of cool transformations to get this awesome result for a really cool looking integral. Yeah, see you next time.